In this video, we'll talk about finding metrics that can be used to find good linear regression models. Recall that there are three things to consider when evaluating models in a regression task. In the last video, we focused on the assumptions of linear regression. In this video, we'll focus on the last two questions. To answer question 2, how much variation in the response does the model explain, we have the R-squared metric in linear regression. R-squared is derived from the following fact. The variance of the response values is equal to the sum of two other variances. The variances of the fitted values from a regression model plus the variance of the residuals from that model. We can describe the variance of the response values as total variation because it is a measure of how much the responses vary. We can describe the variance of the fitted values as explained variation because the fitted values are what our model is able to predict or explain. And similarly, the variance of the residuals can be described as unexplained variation. R-squared provides a direct answer to this question because it is exactly defined to be the ratio of explained variation to total variation. R-squared ranges from 0 to 1, where 1 represents a perfect model and that 100% of the variation in the response is explained by the model. The model exactly predicts our observed responses. This will almost never happen in practice unless something funny is going on. Let's look at an example from the New York housing data. We fit here a linear regression model of house price with the predictors living area in square feet and number of bathrooms. We see from looking at the coefficients part of the output that both living area and bathrooms look like relevant predictors of house price. On average, house price increases by about $93 per extra square foot, holding constant the number of bathrooms. And on average, each extra bathroom is worth about $26,400, holding constant square footage. The p-values for these coefficients are statistically significant at the 0.01 level, which also means that their 99% confidence intervals will be completely above 0. This means that even when considering how our results could change with sampling variability, we could reasonably conclude that there exists relationships between each of these predictors and house price in the target population of upstate New York houses. But have we explained all of why houses vary in price? We look at the R-squared value to answer this, which is reported in R as multiple R-squared. The value is 0.5226, which means that 52.26% of the variation in house prices is explained by this linear regression model. Is 52.26% good? The answer to this is context dependent. In some contexts, data are just highly noisy, and regardless of our efforts to include relevant predictors, R-squared may not be very high. In this case, 52% certainly isn't bad, but we are very likely missing out on key predictors, such as internal quality of the house, school districts, neighborhood characteristics, land size, and parking. We should consider some alternate models. Can we use R-squared to compare models? In general, no. There is a problem with the R-squared metric. If we add another predictor to our model, even a completely uninformative one, the R-squared value will increase. Practically, this means that we cannot use R-squared to compare models that have different numbers of coefficients. What then can we do? There is an alternative to R-squared called adjusted R-squared. Like ordinary R-squared, we want adjusted R-squared to be high. However, adjusted R-squared adjusts the ordinary R-squared from a model to penalize useless predictors. Penalization in this context means that this metric is hurt by having more of what we want to avoid. We want to avoid adding useless predictors, and the adjusted R-squared has a form such that it is hurt. It decreases when we add useless predictors. It's helpful to look at the formula and a numerical example to see how. Let's say that we have a sample size of 50 and our first model with 4 coefficients has an R-squared of 0.5. Using this formula, the adjusted R-squared is 0.4674. Let's say that we fit a model with an additional predictor, which now has 5 coefficients. This model has a higher ordinary R-squared of 0.51, but it has a lower adjusted R-squared than the original model. 4664 compared to 4674. This happens because the number of predictors p appears as n minus p in the denominator here. In fact, because we want adjusted R-squared to be high, we can view this entire last part as a kind of mathematical penalty. Why? Because it is greater than or equal to 0, pause to convince yourselves of this, and it is being subtracted from 1. The penalty has two components. The first component has to do with ordinary R-squared. Adding more predictors will increase R-squared and decrease this component of the penalty. We'll hope that this decrease is enough to offset the second part of the penalty. The second part directly involves the number of predictors. Adding more predictors increases this part of the penalty because more predictors decreases the denominator and the numerator is a fixed positive number. So, adjusted R-squared represents a trade-off between the increase in ordinary R-squared and the number of predictors added. Adding predictors only increases adjusted R-squared if they explain sufficiently more variation than the original model. In this way, adjusted R-squared provides a way to fairly compare models with different numbers of coefficients. In this case, the adjusted R-squared decreased for the new model because the increase in ordinary R-squared was so modest, 0.5 to 0.51. If the increase in ordinary R-squared had been more substantial, say to 0.6, the adjusted R-squared would have increased. Returning to our housing data model, we see that our original model with living area and bathrooms as predictors has an ordinary R-squared of 0.5226 and an adjusted R-squared of 0.522. We add number of fireplaces to the model and see as expected that the ordinary R-squared increases to 0.5232 and that the adjusted R-squared barely increases to 0.5224. So according to the adjusted R-squared metric, a model with fireplaces does explain sufficiently more variation than a model without, but barely so. We actually see that the p-value for the fireplaces coefficient is above our significance level, which we'll say was set to 0.01 beforehand. This is a different but also reasonable line of reasoning. If we want to use p-values as our metric for determining the worth of a variable, fireplaces actually do not merit being added to the original model. If instead of fireplaces we add whether or not the house is on a waterfront, we see that the adjusted R-squared increases more appreciably and that the p-value for the waterfront coefficient is significant at the 0.01 level. Here we have two different but reasonable lines of reasoning agreeing with each other: coefficient p-values and adjusted R-squared. Let's step back for a second and see where we are in answering our questions. We've looked at answers to the question, how much variation in the response does the model explain, with the ordinary and adjusted R-squared metrics. We'll finish this video by looking at a metric to answer the last question, how accurate are predictions from the model? For regression tasks where we model a quantitative response, mean squared error, abbreviated as MSE, is the most common error metric used by machine learning practitioners. To compute it, we compute the residuals for each case, square them, and average them. Hence the name mean squared error. We can interpret MSE as a measure of how far the model's predictions are from the observed values on average. Low MSE corresponds to high average accuracy of the model. So we want models that have high adjusted R-squared and low MSE. Here's an idea. How about we keep trying different models on our data until we have high adjusted R-squared and low MSE? This idea is reasonable at first glance, but we run into a problem called overfitting. Overfitting and combating it are going to be central themes in this course. What is overfitting? Overfitting occurs when we build a model that treats noise as signal, when we build a model that follows the noise in the data too closely. Let's look at a conceptual analogy. Our data consists of this picture of a cat, and we build our model by identifying features. It has uneven black and gray stripes. It has a tail that's a foot long. It has 2 ears that are white in the middle, tan on the perimeter. It has 8 left whiskers, 12 right whiskers. Its eyes are yellow-green. It's lying down. This model has done a great job of predicting this one cat, but it will fail miserably when predicting other cats in other pictures. That is, this model does not generalize to new data well at all. It picks up on the noise too much. It looks too closely at highly individual features of this cat. This certainly helps to explain how more of the pixels explain this particular cat, kind of like increasing R-squared. But these additional features, which are analogous to additional predictors in a model, don't help make a good general model for cats. In regression tests, perfect overfitting can happen when the number of coefficients in the model is equal to the number of cases. Generally, when we have a lot of predictors, we should be concerned about building models that overfit our data. Very shortly in this course, we're headed towards methods for dealing with overfitting in regression settings. In summary, we've gotten answers to our last 2 questions about model quality and usefulness. How much variation in the response does the model explain? R-squared in linear regression is a natural metric for this, but has the problem that it automatically increases with adding any additional predictor, even ones that are not useful. Adjusted R-squared is a penalized version that can be used to compare models with different numbers of predictors. How accurate are predictions from the model? Mean squared error is the most common metric for this. And finally, in the model building process, it's tempting to try lots of models to keep improving these metrics. Exploring isn't inherently bad, but we do need to worry about overfitting. Soon we're going to be learning about techniques to address that issue.